take some time to look at section 2.8, related rates. This is our second section in chapter 2 that addresses applications of the first and second derivatives. Let me start by saying, because this is the first video that will follow this process, if you'll go back to Blackboard, you can find a worksheet to accompany this video. The worksheet will look like this. It's 2 pages, and you can download this from Blackboard. And what this is simply a worksheet of the 5 application problems that will be worked out during this video. You may find it helpful to have that, to print it out to guide you through the work, so you don't find yourself needing to write down, to copy each of the problems as we get to them. So again, you could go to Blackboard to download this worksheet that'll accompany the video. The first question on our worksheet asks us to find the related rate for a hypothetical square. So problem 1 reads, a hypothetical square grows so that the length of are increasing at a rate of 9 meters per minute. How fast is the area of the square increasing when the sides are 3 meters each? Well, to start with, any problem of this nature, I'm going to begin by drawing a sketch of the geometric figure. In this case, the sketch of this square. I'm also going to define the variables. We're going to let S equal the length of the side and let T represent the time. The next step is to write a function for, and how I know what function I want to write. I want to write a function for whatever the question is asking. So a function of the area, and this is saying the sides are increasing at 3 meters each. So I'm going to find a function for the area of a square with respect to the length of side, the A with respect to S, or A of S. Now the area of a square is the side squared, so here's our function. Reading this problem again, I see that what I'm given is that the change in the side with respect to time, so ds dt is 9. And I can read this problem to find that what I'm trying to find is the change in the area with respect to time when the length of the side is 3. So the next step to these problems after writing the function is to write what we're given and what we're trying to find. So let's write out what we're going to work through. We want to find the derivative of the area with respect to time. Now you'll see from the function we have area with respect to S, and we want the derivative of the area with respect to t. So it's not asking us to find dA ds, it's asking us to find dA dt. So to do that, I'll find the derivative of the area with respect to S and multiply that by the derivative of S with respect to t. The derivative of area with respect to S is simply the derivative of our S squared, so 2S. And the derivative of S with respect to t we were given, and that was 9. So our derivative of area with respect to t will be 18s, and the derivative of area with respect to t when the length of the side is 3 units long will be 18 times 3, or 54 meters per second squared. Very important practice to finish a problem by writing out a therefore statement. So I'm going to say therefore, here's a mathematical symbol for that word, therefore the area increases at a rate of 54 meters squared per second. Problem 2. I'll read that aloud. Oil spilling from a ruptured tanker spreads in a circle on the surface of the ocean. The radius of the spill increases at a rate of 3 meters per minute. How fast is the area of the spill increasing when the radius is 9? Following the same process I used for question number 1, I'm going to start by drawing a circle and labeling the variables. Let R represent the radius and T represent the time. And then I can write a function for the area with respect to the radius, pi times radius squared. I want to find the derivative of the area with respect to time. That's what the question asks for. And I'm given that the derivative of the radius with respect to S is 3. So the derivative of area with respect to T, with respect to time, is going to be the derivative of area with respect to R, dA dr, times dr ds. Well, I can find the derivative of area with respect to R up here. The area is pi r squared. Then the derivative is 2 times pi r to the 2 minus 1, or just 2 pi times radius. I'm given the derivative of r is 3, so by multiplying those, I get 6 pi r squared. The derivative of the area with respect to t when the radius is 9 is 6 pi times 9, or 54 pi meters squared per minute. Good practice is to write that the area of the spill is increasing at a rate of 54 meters squared per minute, or in other words, to answer the question. The third question reads, the hypothetical cube grows so that the length of its sides are increasing at a rate of 2 meters per minute. How fast is the volume of the cube increasing when the sides are 4 meters each? So I've drawn the cube and I've labeled the variables. Let S equal the length of the side and T equal the time. I've written a function. The volume of the cube with respect to the length of the side is side cubed. I'm given that ds dt is 2, and I want to find dv dt when S is 4. By the way, I realize I'm moving rather quickly through these examples. You may find it helpful to pause and replay as needed. We want to find the derivative of the volume with respect to time when the length of the side is 4. So I can write out that the derivative of volume with respect to time using the chain rule is dv ds times ds dt. So we get dv ds, 3s squared, ds dt is 2. Multiplying those together with the chain rule, we have 6s squared. So the derivative of the volume with respect to time when the side is length 4 would be 6 times 4 squared, or 96 meters cubed per minute. Problem number 4. Water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 3 centimeters per minute. How fast is the area of the pool increasing when the radius is 4 centimeters? Following the same process, I've drawn a circle and labeled the variables. Let R represent the radius and let T represent the time. And I have that the area with respect to R is pi r squared. We're given dr dt is 3 and dA dt when the radius is 4 is what we're trying to find. So I can find the derivative of area with respect to time by applying the chain rule. So the derivative of area with respect to R, the radius, times the derivative of the radius with respect to time. The derivative of the area function is 2 pi r, and dr dt was given as 3. Multiplying those together, we get 6 pi r. Substitute in r equals 4 to find the derivative of area with respect to time when the radius is 4, and I'll get 24 pi. Thus, the area of the circular pool is increasing at a rate of 24 pi centimeters squared per minute. One more problem, number 5. This question is going to involve a little bit of geometry. We have a hypothetical square growing so that the length of its diagonals are increasing at a rate of 7 meters per minute. How fast is the area of the square increasing when the diagonals are 10 meters each. So I've drawn a square and I've labeled the S for side and the D for the diagonal. And then we need T for time. Notice that we need to come up with a way to describe the area with respect to a diagonal. This isn't a formula that I know, but I do know the area of a square with respect to side is area equals side squared. And I know the Pythagorean Theorem, side squared plus side squared equals a diagonal squared. A squared plus B squared equals C squared. So I can use these two formulas to first start and find a way to represent S with a D. So the 2S squared equals D squared. Dividing by 2, S squared equals D squared over 2. Square rooting both sides, I get D over the square root of 2. I don't have to worry about the plus or minus here because the side can't be a negative length. So I can take this side, D over the square root of 2, and say that the area with respect to the diagonal is the side squared, or D over square root of 2 squared. When I square D over the square root of 2, I get D squared over the square root of 2 squared, or just D squared over 2. And now I'm on my way. Given that the derivative of the diagonal with respect to time is 7, I can find the derivative of the area with respect to time when the diagonal is 10 meters long. dA dt is going to be dA dd times the derivative of the diagonal with respect to time. So we have 1/2 of 2 times the diagonal times our given 7, or just 7d. When I let d equal 10, I'd get that dA dt when d equals 10 is 7d. Therefore, the area increases at a rate of 70 meters square per minute.